All right, and let's start then looking at projectile motion, which is just like one-dimensional motion, the one-dimensional motion we looked at last week, but now it's happening in 2 dimensions. What we'll do is we'll take each of those dimensions one at a time, look at it independent from the other one, and what happens is a projectile motion question basically becomes two questions of the type you did last week with motion in one direction. Okay? So again, this projectile is moving in 2 dimensions. We'll look at the vertical and use the equations we used last week. We'll look at the horizontal and use the same equations again. We'll put them back together at the end if necessary. All right? And so the first thing we should talk about is acceleration due to gravity. If an object is falling, it will accelerate at 9.8 meters per second squared downward. And that is independent of its mass, because as its mass goes up, the force of gravity increases as well and causes the object to accelerate at the same rate. This happens if we ignore air resistance, which for our purposes we will, and that's a valid assumption to make if the object is not moving really, really fast, because air resistance increases with velocity. All right, so if the object is thrown upward, it'll climb, its velocity will be upward, and it'll continue to climb until its velocity reduces to 0, and then the object will be at its peak height. Now, since acceleration is constant, when the object reaches the height that it was launched from, that is like when the ball returns to your hand or when the bullet comes back to the ground if you're shooting a gun up in the air, its velocity downward will be the same as its original velocity upward. Again, that's true if we ignore air resistance. And here are some examples for you to look at. And when we're looking at a projectile motion question, it's important to note that we'll deal with the horizontal motion separate from the vertical motion. And that makes it easier because in each case we can just use equations of one-dimensional motion, the same ones that we were using last week. We can put them together later at the end. But essentially, a projectile motion question is just two questions from last week put together. That data that you get between the two directions is linked by time. Now, the following is something that people get confused fairly frequently. First, when you're dealing with horizontal motion, because we're ignoring air resistance, and because there are no other forces acting on a flying object horizontally, acceleration is 0. So whatever velocity your object starts with, it'll also end with. Vertically, however, your acceleration is 9.8 meters per second squared because it's gravity that's working on this object in the vertical frame. And we'll deal with, in our studies, we'll deal with two initial conditions. One where we launch an object horizontally, say off the edge of a table or off a cliff, and two, where we launch at an angle from the horizontal. So number one might look like this, with number two looking like this. Now, if we break the horizontal component away from the vertical component, here's what it looks like. Imagine you were looking down from above. That's an eyeball, by the way. You're looking down from above. The object, if you couldn't see depth, you couldn't see that the object was coming up towards you and back away. The object would appear to move in a straight line across the surface of the Earth at a constant speed. So horizontally, see this person here can't see what's going on vertically with this flying object. It can only see that it's moving across the surface of the Earth. Now, that's the horizontal motion. Vertically speaking, here's another eyeball. Vertically speaking, if this person couldn't see that the ball was coming towards them, then what they would notice is, at first, the ball travels quite a long ways in a given time period, and later on, it moves less in a given time period. That is to say, it slows down. Eventually, it'll come to a peak, and it'll start coming back down again. What this person sees is this object just traveling straight up and straight down. Again, if they can't see depth, so they couldn't see that the ball was moving towards them. We're separating horizontal from vertical. All right, so here's one type of question setup that you will see in the questions you'll have to deal with in this part of the course. In this case, the projectile is launched from some elevated location. It's launched horizontally, the assumption being that the ground over here is horizontal. It's launched horizontally and falls some way. Now again, in the horizontal, there won't be any acceleration, so the horizontal velocity will be constant. In the vertical, there will be an acceleration, which will be equal to 9.8 meters per second squared. And so this is another important point. In these situations, initial vertical velocity is going to be 0. That is to say, when this object just leaves the cliff right here, that very split second when it leaves the cliff, it's not moving up or down yet. Again, because we assumed this cliff to be vertical, this surface to be vertical, at the moment of launch, the object is only moving horizontally. Afterwards, it does pick up a downward velocity, but initially its velocity is 0. So it's v1 equals 0. Horizontal velocity is constant, and so v1, let's stick a y in here to distinguish it from the horizontal velocity. v1x is constant, so we can just refer to that as vx. There's no v2x. And because motion is downward, it makes sense to make the downward direction positive. That is to say, make this 0 and make downward from there positive. The reason being is this never gets above this 0 height. We never go above here. So we never have to deal with negatives if we do this. It's still possible to call this negative and you'll do just fine. It's just a little bit more complicated, and maybe you don't want to complicate things for yourself. And so from this setup, you could be asked to find the time of the flight, which is a vertical question. It's vertical because really what you want to know is how long, given your v1 of 0 in the vertical, how long does it take to fall from this height? Conversely, you could be asked to find the initial height of the projectile, which is really just the same question, but with different given information. Here, you'll know the height of the cliff. In this question, number 2, you'll know the time it takes for it to fall that distance, and you can calculate height that way. 3, you could be asked the horizontal distance of the projectile, that is, the distance from the edge of the cliff to where it lands. Or you could be asked to find the initial horizontal speed of the projectile given that it flew a given some distance. So you know that delta dx, and you're tasked with finding how far did it, or how fast was it going initially. Now, in questions 1 and 2, again, this is a vertical. These are vertical questions. We ignore the horizontal component of the motion, and we'll calculate either time or height, because we'll be given the other one, as if it was just, this object was just dropped vertically and was traveling straight down. Because really, if we ignore the horizontal component, if we're just viewing from over here, then that's all that's happening vertically. And here's what we do, here's how we find that. Delta dy equals 1/2 a delta t squared. And so given d, delta d, we can find delta t squared, and then we can find delta t. That's a delta t squared. Or if you're given the time that it takes to fall that distance, then we can find delta d just by plugging that in and solving for delta d. If you're asked how far away the object lands from the cliff or from the edge of the table or whatnot, this is a horizontal question, and in these cases, questions 3 and 4, on 2 slides back, we will ignore the vertical, we'll ignore what's going on with the vertical, and we'll use this equation over here to either find distance, horizontal distance, or in horizontal velocity, or the time will come from the previous type of question. That is, the time it has to travel horizontally is the time it takes to fall from here to here. So it can travel horizontally for the time it takes to reach the ground. All right, let's look at an example where a pool ball leaves a 0.6 meter high table with an initial horizontal velocity of 2.4 meters per second. Predict the time required for the pool ball to fall to the ground and the horizontal distance between the table's edge and the ball's landing location. So this question comes in 2 parts. First, the time required for the pool ball to fall to the ground. That's vertical. And next we'll be finding the horizontal distance between the table's edge and the ball's landing location. As you can tell, that will be horizontal. So let's make this 1, make this 2. All right. In order to find the horizontal distance between the table's edge and ball's landing location, let's draw a diagram here. That's part 2. The reason, in order to find that, we'll need to know how long it flies for. How long is it in the air for? So we're going to be looking like this. Delta D equals V1 delta T. And in order to do this, now we have the velocity, we don't have time. How long can it travel horizontally for? Well, in order to find time, we need to figure out how long it'll take before it hits the ground. Because as long as the ball is traveling on its way to hitting the ground, it can be moving horizontally. After that, it stops. All right, and so to find the answer to 1, how long will it take the ball to fall to the ground, we can know that the acceleration will equal 9.8 meters per second squared because it's accelerating due to gravity. We know that the v1 of the ball vertically speaking, will be 0. Again, it'll be 0 because the surface of this table will assume to be horizontal, and the ball will be following that surface because it's rolling along it. And so at the moment it leaves the surface of the table, it will be traveling horizontally. Thus, its vertical velocity will be 0. The other thing we know is that in the vertical, this pool ball will be making 0.6 meters of displacement. It'll be displacing itself or moving 0.6 meters. And so, solving one with all that information we have from the previous slide, we can use this equation. We want to know how long it'll take for the ball to get to the ground. Delta D equals V1 delta T plus a half A delta T squared. Now, this is an equation that you used from the questions from last week. We have displacement, that's the height of the table, that's how far it falls vertically. We have V1, we have A, we're looking for delta T. Now, if you look at this, this is a quadratic in T. There's a T squared and a T and some constant. However, because our V1 equals 0, this whole first term becomes 0, and it simplifies things greatly for us. And so because V1 is 0, this simplifies to delta D equaling a half A delta T squared. Solving for delta T then, we need to get rid of this half and A first. We'll have delta D divided by 1/2 or 0.5 and also divided by A. That's delta T squared. And then delta T will just be the square root of all of that stuff. Delta D over a half A. All right, here we'll substitute in our values going up this way. Delta T equals the root of 0.6 meters over a half times acceleration is due to gravity, so it's 9.8 meters per second squared. And a half, this works out to 0.6 divided by 4.9. Take the square root of that, you get delta T equaling 0.35 seconds. You actually get 0.3499 something. A lot of decimal places there. It rounds to 3.5. My suggestion would be that you take that and you don't round it. You write it as 0.35 if you want, but store the figure in memory as 0.3499, whatever you get, and use that unrounded figure in your calculations round at the end. That would be my advice to you. So delta T equals 0.35 seconds. This is the first part of the question we're asked to find. The second part of the question asks us to find the horizontal distance from the edge of the table to the ball's landing location. And so here's our table. Here's the path of the ball. we need to find this distance here. We know that vertically the v1 is equal to 2.4 meters per second in the direction that we're going. We have a delta t now of 0.35 seconds. It's traveling toward its landing location for as long as it takes for the ball to fall, because when the ball reaches the ground, it's reached its landing location. We need to find its vertical displacement here. And so here's the equation that you know from last week, delta v equals delta d over delta t. Rearranging, that's not a zero, by the way, that's a need to know it. Rearranging, we have delta d equals v1 delta t. Plugging in our values, 2.4 meters per second in whichever direction we happen to be traveling, times 0.35 seconds. Seconds cancel. We're left with units of meters, equals 0.83 meters in the direction which we're traveling. In the second type of question we'll be dealing with, a projectile is launched at some angle to the horizontal and rises upward to a peak while moving horizontally. So vertically it's rising and then falling, rising and then falling. Horizontally, this object is just traveling straight across at a constant velocity. There are a number of questions you could be asked about this scenario. Some of them are time of flight, that is, how long will it take for the ball to go up and come all the way back down? To the height of the projectile at its peak, you might be asked for peak height. You might be asked for the horizontal range, that's how far does this ball fly. Or, if there's some obstruction at some distance, there, how high is the ball when it reaches that obstruction? Should be noted here in these types of questions, again, because we're never going to drop below our launch pad, up is a good direction to make positive in. Even if we're launching from some sort of cliff and allowing the ball it still makes more sense to make up positive. Now, in order to do this type of question, in order to separate vertical from horizontal, we need to take its initial velocity, which is given as the radar gun velocity measured at whatever angle it's traveling at. So our initial velocity is given as this, not as a horizontal or vertical. We need to separate that velocity into its x and y components. So this would be called v1x. It'll also have an initial vertical component of v1y. And as you can see, this is a right angle triangle, and if that's the case, we call this angle theta. Then v1y will equal v1 times the sine of theta, Why is that? Because the sine of theta will equal the opposite side on the triangle divided by the hypotenuse, that is to say the lengths of those sides. The opposite in this case is v1y, over v1. These get vector symbols all around. Sine theta. And because sine theta equals v1y over v1, we can rearrange that to solve for v1. For v1y. And v1y, multiply both sides by v1, will equal, after these cancel, v1 sine theta. For the same reason, but using cos, v1x equals v1 cos theta. This is true if this, the angle between the launch velocity and the horizontal, is given. If you happen to be given the other angle over here, right over here, then sine and cos end up being reversed. This is the angle you'll typically be given. But do be aware that these aren't absolutes. These are based on the relationship between this angle and the sides of the triangle that you're dealing with. And if you're not given that angle, if you're given some other angle, the relationships may change. In the first type of question, where we're asked to find the time of flight, we can ignore the horizontal component. All we need to do is find v1y. We can not use v1x for now. However, we do have to break the initial velocity, which will be in the direction of travel. The initial velocity won't be the figure we need. Here's initial velocity. Here's v1y. Here's v1x. In this type of question, you'll be given a v1, and the first thing you do, break it into x and y components. After that, you use v1y with the vertical stuff, use v1x with the horizontal stuff. All right, the way to deal with this question, there's many ways to deal with the question. One way to deal with the question is to recognize that when the ball leaves, it'll have a certain vertical velocity, v1y. It'll take some amount of time to get to the peak. And at the peak, its velocity will be 0. So let's, for the purposes of this discussion, call acceleration due to gravity just 10 meters a second. Let's say that this height is 30 meters. So you launch with v1y. Initially, this ball has velocity of 30 meters a second upward. After 1 second, say right here, it'll have a v of 20 meters a second because you're accelerating at 10 meters a second downwards. So every second, your velocity drops by 10 meters per second. You were going 30 initially. After 1 second, you're going 10 meters per second less than that. And another second goes by, and you're going now 20 minus another 10 meters a second. So now, after 2 seconds, you're only going 10 meters a second. And after 3, you're going 0, because you've just lost another 10 meters per second. After 3 seconds, your velocity is 0. Because your velocity is 0, you're no longer traveling upward, and that means you've reached the peak. Now, if it took 3 seconds to get up there, it'll take 3 seconds to get back down. And so, this object, which is at 0, after 1 second, will increase its velocity to 10 meters per second. That's what 10 meters per second squared means. Every second, you're gaining 10 meters per second. So after 1 second, you're going 10. After 2 seconds, you're going 20 meters per second. After that third second, you're going 30 again, but in the opposite direction. So v2y then equals negative v1y. All right, in question 2, the second type of question, where we're asked to find the height of the projectile at its peak, we have to recognize that at its peak, the velocity of the object becomes 0. Why is that? Because if the object were still moving upward, if it had a positive velocity, then it wouldn't be at its peak yet. If its velocity were downward or negative, then it would have already been at its peak. And so at at peak, it's important to recognize that v2 equals 0. In the third type of question, where we're asked to find the horizontal range of the object here, this is a question in the horizontal, so we're going to ignore the vertical component, except for we're going to use it to find the time it takes to hit the ground again. So this this third type of question involves question 1 first. So find the time of flight That's happening in the vertical. And then, over that time, it's traveling horizontally at its initial v. We can find delta d in the x being equal to v delta t. In the fourth type of question, we're asked to find how high is the object when it hits some obstruction some number of meters away. This could be a batter hitting a ball, and the ball finally gets to the wall, and does it clear the wall, or how high up the wall does it hit? Or it could be a hose or something launching water at some angle, the angle being theta. And how high up the wall does it hit? You could ask it a bunch of different ways. But the way to deal with this is to first figure out how long it'll take that projectile to reach the wall. And rearranging rearranging v equals d over t, delta t will equal delta d divided by v. So delta dx divided by our vx. In order to find vx, we'll need to break our initial v into horizontal and vertical components. Once we have the t, we can plug that t in, and using this equation, delta dy equals a half a delta t squared, we can find how high vertically the ball is at the time we just found. And so let's do an example of that type. this question says a ball is kicked with an initial velocity of 25 meters a second at an angle of 45 degrees with the horizontal. Determine the time of flight, the horizontal displacement, and the peak height of the football. The first thing we have to do in this type of question is break the initial velocity, which is at an angle of 45 degrees, into its horizontal and vertical components. This is v1x and v1y. And as we discussed before, v1y will equal v1 times the sine of theta, which in this case is 45. Our initial velocity is 25 meters per second. And so v1y will equal 17.68 meters per second up. This being a 45-degree angle, we'll know that these two sides will be equal, but in case you didn't notice that, then v1x would be equal to v1 cos theta, which in this case again is 45 degrees. And if you do the math, that also equals 17.68 meters per second, this time to the right. And so we're asked to find time of flight first, and we can do that. A time of flight, that's a vertical question. And what the question asks is, how long does it take for the velocity to go from v1, we just figured our v1 vertical to be 17.68 meters per second. How long does it take from our vertical velocity to go from v1 to negative v1? Because again, when we reach the same height, we're assuming horizontal ground here, when we reach the same height of 0, the ball will have the same velocity that it started with, but downward, not upward. So we have a v1 of 17.68 meters per second up. Our v2 equals 17.68 meters per second down. Now, when we plug these into an equation, we want the directions to match. These two directions need to match. Now, in order to do that, we can, because these directions are opposite, we can say that v2 equals negative 17.68 meters per second up. Always when we work in the vertical, acceleration is equal to 9.8 meters per second squared down. But because we're working in the positive, you could just as easily work in the negative. No, it's probably a little bit harder, but it's still possible. Because acceleration is down and we've chosen up to be positive, acceleration is going to be equal to negative 9.8 meters per second squared up. And so we have v1, we have v2, we have a, and we're looking for delta t. And so if we look at the equations that we have, we see that we have this one, v2 equals v1 plus a delta t. And we could say we could rearrange that, sorry. We could rearrange that to say that delta t equals v2 minus v1 over a equals v2 being negative 17.68 meters per second minus v1, which is 17.68 meters per second, divided by negative 9.8 meters per second squared. Notice that v1 is negative. We're subtracting the positive, sorry, v2 is negative. We're subtracting the positive v1 and dividing by the negative acceleration. So the numerator here will be negative. The denominator will also be negative. We'll end up with a positive answer. It's quite common for people to forget that acceleration is going to be negative in this case. And people will end up with a negative time. Hey, what's going on here? You can't have a negative time. Well, of course you can't. You've just missed a sign there. And so doing the math, negative 17.68 minus 17.68 divided by 9.8, this of course has to happen first, right? We get an answer of 3.61 seconds. So delta t equals 3.61 seconds. In the third part of this question, we're asked to find the horizontal distance. How far does this ball travel before it lands? Now, we just found out that we have a delta t, a total flight time of 3.61 seconds. We're looking for a horizontal distance, and so we'll be using our v1x, which is 17.68 meters per second to the right. And because there's no acceleration in the horizontal, this will equal v1. It's just equal to v1. To vx. There's no 1s and 2s about it because there's only one velocity. And so we're looking for delta d. You know this equation. When there's no velocity, when there's no acceleration, v1 equals delta d over delta t. And rearranging, delta d equals v delta t equals 17.68 meters per second to the right times 3.61 seconds, which gives us a horizontal distance of 63.82 meters in the direction we're traveling. Let's also ask ourselves, if this ball were kicked only, let's say it were kicked 40 meters from some wall, and we want to know how high up the wall it hits. So how high up the wall it hits. First, what we're going to do is figure out the time it takes to go this 40 meters. So how long will it take to make that distance? Second, we'll plug that distance into a vertical equation and figure out how high off the ground will we be at that time. And so, first we'll work in the horizontal, and we know that Vx equals delta dx, in this case 40 meters. divided by delta t equals delta d x over vx. These all have vectors. And using our initial velocity of 17.68 meters per second, velocity in the x direction of 17.68 meters per second to the right, we get a figure of 2.26 seconds. And next what we're going to do is we're going to take that 2.26 seconds and we're going to figure out at that time how far is the football from the ground. So let's change pages and do that. All right, the second part of that says if it takes 2.26 seconds to get to the wall, how high is the ball by the time it gets there at a time of 2.26 seconds with, or given that it had a velocity vertically of 17.68 meters per second meters per second up, and given that it is accelerating at 9.8 meters per second squared down. Now, when we plug these figures in, acceleration and velocity, if we're plugging them into the same equation, the directions have to match. So we're going to call that up. But because the acceleration is actually down, the opposite of up, it gets a negative sign. And so we can say that delta d, given that we have delta t, v1, y, and a, looking at our equations, we see that this one, v1 delta t, plus a half a delta t squared is one way to find our displacement at that time. And so, substituting, we have 17.68 meters per second times 2.26 seconds. Seconds will end up canceling there. What we're going to do, because of the order of operations, this is going to be simplified, this is going to be simplified, and then we add the two together. Plus a half, negative 9.8 meters per second squared. Don't forget that negative, people often do. Times 2.26 seconds squared. In this part, the second part, here you're going to have units of seconds squared multiplied by meters per second squared. The seconds squared are going to cancel. Again, you're going to end up with units of meters, which is good because we're adding them to meters. And we're looking for displacement, which comes in units of meters. This first term equals out to 40 meters. That's how fast, that's how far it would have traveled if there was no acceleration. However, because there is an acceleration, that number is different. We get an answer of negative 25.1 meters. And that gives us, this is rounded. Just for writing though, I left the whole number in my calculator and subtracted that whole number from 40, the unrounded number from 40, to give us 14.92 meters. And so at a time of 2:26, which is the time it took for the football to get to that wall 40 meters away, this ball will be 14.92 meters in the air. And so, going back to our diagram, this football has been kicked, it's past the peak, and the height of the wall that it hits is 14.92 meters.